The universe is not indifferent to your ambitions. It is not neutral. It does not simply ignore the desire to cross the space between stars. It actively, mathematically, and with absolute geometric precision makes it impossible. That is not a poetic exaggeration. That is a statement derived from the most precisely tested equations in the history of science. And today I want to walk you through exactly why the stars, despite being visible on every clear night, despite feeling almost reachable when you stare at them long enough, are separated from us by a barrier that is not made of distance alone. The barrier is woven into the very structure of space, time, mass, and energy. It is not an engineering problem. It is not a funding problem. It is a problem written into the mathematical foundation of physical reality itself. Let us start with the number that governs everything: 300 million meters per second. That is the speed of light, and it is not merely fast. It is the absolute speed limit of the cosmos. Nothing with mass, no particle, no atom, no spacecraft, no human body can reach it. Not because we lack the technology, because the mathematics of special relativity forbids it with the same categorical certainty that 2 plus 2 forbids you from arriving at 5. To understand why, you need to understand what happens to mass as it moves. Imagine you are pushing a boulder across a flat surface, and with every single step you take, that boulder doubles in weight. After 10 steps, it weighs 1,000 times what it weighed when you started. After 20 steps, it weighs 1,000,000 times more. After 100 steps, the boulder is heavier than the entire planet beneath your feet. No amount of force you can apply will accelerate it further, because the harder you push, the heavier it becomes, and the more energy you pour into it, the more its resistance to acceleration grows in perfect lockstep. That is exactly what happens to a spacecraft as it approaches the speed of light. This is not a loose analogy. This is the mathematical reality described by the Lorentz factor, a term in Einstein's equations that governs how mass behaves at relativistic velocities. As a massive object accelerates toward the speed of light, its relativistic mass increases without limit. At 10% the speed of light, the increase is negligible. At 90%, you already need vastly more energy to accelerate than Newtonian physics would predict. At 99%, the relativistic mass of your spacecraft has ballooned to roughly 7 times its rest mass. At 99.9%, it is over 22 times heavier. At 99.99%, it is over 200 times heavier. And as you push toward 100% of the speed of light, the required energy approaches infinity, not a very large number. Infinity. There is no energy source in the universe, no matter how exotic, that can supply an infinite amount of energy. The universe itself does not contain enough energy to push a single proton all the way to the speed of light. This is not a limitation we will engineer our way past. This is the universe telling you, in the language of mathematics, that the answer is no. Now let us talk about the stars themselves, because even accepting that we cannot reach light speed, you might ask whether we can get close enough to make the journey feasible. The nearest star system to our own is Alpha Centauri, sitting at a distance of approximately 4.37 light years. A light year is the distance light travels in a full year, roughly 9.46 trillion kilometers. At the fastest speed any human object has ever traveled, the Voyager 1 probe moving at about 17 kilometers per second, reaching Alpha Centauri would take approximately 73,000 years. So the question becomes, can we do dramatically better? Can we build a spacecraft that reaches, say, 10% of the speed of light, or even 1%? And the answer, in principle, is not physically forbidden. But what it demands in terms of energy and engineering is so far beyond anything we have ever attempted that it might as well be. Consider the energy budget. To accelerate a spacecraft of modest mass, let us say 10,000 kilograms, roughly the mass of a small bus, to just 1% of the speed of light, you need approximately 4.5 times 10 to the power of 17 joules. That is about 450 petajoules. The entire annual electricity consumption of the United States is roughly 14 petajoules. You would need 30 times the annual electrical output of the entire United States just to push a bus to 1% of the speed of light. And at that speed, the trip to Alpha Centauri would still take 430 years. Push the spacecraft to 10% of the speed of light, which sounds much more promising, and the energy requirement scales with the square of the velocity. You now need roughly 100 times more energy than for 1%. You are looking at an energy budget that dwarfs the total output of every power plant on Earth over centuries. And the trip to the nearest star still takes over 40 years. For a round trip, 80 years, no human crew survives that mission. No current technology, or technology that is even theoretically within reach, can generate that power. But energy is not even the most violent problem. The most violent problem is what the journey does to the ship itself. Interstellar space is not empty. This is one of those facts that sounds obvious once you hear it, but the implications are genuinely catastrophic when you work them through. Between the stars, space is filled with what physicists call the interstellar medium. It is extraordinarily sparse. It averages roughly 1 hydrogen atom per cubic centimeter, along with microscopic grains of dust, ice particles, and trace elements scattered at almost unimaginable densities. At everyday speeds, this is completely irrelevant. At relativistic speeds, it becomes an annihilation field. Here is why. Kinetic energy scales with the square of velocity. A particle moving at twice the speed has 4 times the kinetic energy. But at relativistic velocities, the scaling becomes far more severe because the relativistic mass of the incoming particle is also increasing. When your spacecraft is moving at 90% of the speed of light relative to the interstellar medium, every single hydrogen atom it encounters is not a passive wisp of gas drifting past your hull. From the perspective of your ship, that atom is a high-energy cosmic ray striking your hull at 90% the speed of light. Now consider this. A single hydrogen atom impacting your hull at that velocity carries kinetic energy comparable to a high-velocity bullet. That sounds manageable until you remember that at 90% of light speed, your spacecraft is sweeping through roughly 270 million meters of space every single second, and in every cubic centimeter of that space, there is at least 1 hydrogen atom. Your ship is encountering billions of hydrogen atoms per second, and each one is depositing bullet-equivalent kinetic energy into your structure. The dust grains are worse. A microscopic dust grain, something on the scale of 1/100th of a millimeter, impacting your hull at 99% the speed of light, carries kinetic energy comparable to a thermonuclear weapon. Not a conventional explosive. A thermonuclear weapon. A single speck of dust that you cannot see, that you almost certainly cannot detect in time to avoid, detonating against your hull with the energy of a hydrogen bomb. The faster you travel, the more catastrophically the interstellar medium is weaponized against you. The universe does not simply resist your speed. It turns the fabric of space into a bombardment. You cannot shield against this effectively because any shield dense enough to absorb relativistic impacts adds mass to your vehicle, which increases the energy you need to accelerate it, which means you are chasing an increasingly expensive problem in both directions. And you cannot steer around the particles because they are everywhere, and your reaction time at those speeds is essentially zero. Now, there is a concept that captures people's imagination at this point, which is time dilation. Einstein showed that a moving clock runs slow relative to a stationary one. At high enough velocities, a crew traveling at 99% of the speed of light would experience time passing at roughly 1/7 the rate that Earth-bound observers do. At 99.99%, time for the crew passes at roughly 1/224th of the external rate. In principle, a crew could travel to a star 20 light-years away and experience only a fraction of a year on board, while 20 years passed on Earth. This is real. It is not science fiction. The mathematics are unambiguous, and the phenomenon has been directly measured with atomic clocks on aircraft and satellites. But time dilation does not solve the problem. It only changes who ages during the journey. The energy requirements are unchanged. The relativistic mass problem is unchanged. The interstellar medium bombardment is unchanged. The spacecraft still has to be accelerated to those velocities, still has to be decelerated at the other end, using the same impossible quantities of energy. Time dilation simply means that if you could somehow solve every other problem, the crew might not die of old age during transit, but you still cannot solve the other problems. and deceleration is its own crisis. People often think about the acceleration phase of an interstellar journey and forget that you have to stop at the other end. Every ounce of energy you spent accelerating the ship to cruising velocity, you now have to spend again in reverse to slow it down. Your total energy budget doubles. Whatever impossible engine brought you up to speed has to run in reverse, or you fly through the target star system in a fraction of a second and continue into the darkness beyond. There is one propulsion concept that physicists take somewhat seriously for reaching a small fraction of the speed of light, which is the laser sail. The idea is to leave the engine at home and push a very thin, very lightweight sail with an extraordinarily powerful ground-based laser array. The Breakthrough Starshot initiative proposed using a laser array of about 100 gigawatts to push gram-scale spacecraft to 20% of the speed of light. At 20% of light speed, the trip to Alpha Centauri takes roughly 20 years. Not centuries, not millennia, 20 years. But the spacecraft in this scenario has a mass of a few grams. It is essentially a microchip attached to a postage stamp. It can carry no crew, no life support, no scientific payload of any significance, and no deceleration mechanism. It will fly through the Alpha Centauri system at 20% of light speed and continue into space forever, unable to stop, unable to return, transmitting a few photons of data back across 4.37 light years, where the signal, even traveling at the speed of light, takes 4.37 years to arrive. That is a remarkable achievement for exploration. It is not interstellar travel in any meaningful human sense. The deeper you examine this problem, the more clearly you see that it is not a problem at all in the engineering sense. Engineers solve problems by throwing resources at them, by iterating designs, by developing new materials. What we are facing here is a set of mathematical constraints imposed by the geometry of space-time itself. The speed of light is not a speed limit in the way a posted sign on a highway is a speed limit. It is the rate at which the universe propagates causality. It is built into the structure of space and time at a level more fundamental than matter and energy themselves. Einstein's special relativity does not describe a law that some future civilization might find a loophole in. It describes the geometric relationship between space and time, a relationship so foundational that violating it would not merely require new technology, it would require a different universe with different mathematical axioms. The stars are not far away in the way that Australia is far from Europe. The stars are separated from us by a kind of distance that is qualitatively different, enforced not by logistics but by physics. There is a certain profound austerity in confronting this. We live on a pale blue point orbiting an ordinary star in an outer spiral arm of a galaxy that contains several hundred billion stars, within a universe that contains several hundred billion galaxies. The cosmos is, by every measure, incomprehensibly vast, and the laws of nature that govern every particle, every wave of energy, every structure from subatomic to galactic scale, those laws draw a firm, mathematical circle around the small region of space we can ever realistically inhabit. This is not a tragedy, it is a fact. And facts, even austere ones, carry their own strange beauty when examined clearly. The universe is not hostile to life. It is simply indifferent to life's desires, and the indifference is perfectly consistent and perfectly principled. The same equations that make interstellar travel essentially impossible also made the carbon in your cells, forged the iron in your blood inside a dying star, and stretched the geometry of space-time far enough apart that galaxies could form and spiral into the precise configurations you see when you look up on a clear night. The physics does not lie to you. It does not offer false promises. It tells you with extraordinary precision exactly what is and is not possible within the boundaries of this universe. And one of the things it tells you, with the quiet certainty of an equation that has never once been proven wrong, is that the distance between stars is not a challenge to be overcome. It is a boundary written into the fabric of reality itself.